Okay.
Thanks, Charlotte.
All right. So today we're going to be hearing about the recently completed atomic field campaign. We're very happy to Chris Fairall and Hyodae. Brief introduction for each of these speakers. I'm going to read exactly what Chris sent me because it's very nice. Chris Farrell is a physicist at NOAA's Earth System Research Laboratory in Boulder, Colorado, where he heads the Boundary Layer Observations and Processes team. He works on unraveling the mysteries of how the ocean and atmosphere battle as part of Earth's climate system from El Nino to hurricanes. He has spent decades developing and deploying air-sea interaction observing systems for NOAA ships and aircraft and has participated in nearly 70 research field programs. So that last part is just amazing to me. So we're delighted to have Chris share some of his insights on atomic with us. Hyodae received his PhD in oceanography in 2007 from Scripps. He was a NOAA Climate and Global Change postdoctoral fellow, spending time at UCLA and Hawaii. He's currently an associate scientist with tenure at Woods Hole Oceanographic Institute. His particular focus is on how ocean physical processes affect surface fluxes, both in coastal and open ocean regimes. He is co-chair of the U.S. CLIVAR Working Group on Mesoscale and Frontal Scale Ocean Atmosphere Interactions and Influence on Large-Scale Climate, and he is a former member of our very own panel. So it's great to see you again, Hyodae, and we will hear from about 15 minutes, 12 to 15 minutes from both Chris and Hyodae, and then we'll go to the question and answer session. So I'll give you, I'll break in with about an 11-minute warning just to give you a sense of where you are on your time. So let's see, will we hear from Chris or Hyodae first?
Okay, well, so we'll hear from me first. Hyodae is driving. So Atomic is the Atlantic Tradewind Ocean Atmosphere Mesoscale Interaction Campaign, studying shallow convection and shallow convective clouds and ocean coupling in the North Atlantic. The field campaign was associated with the Eureka European Field Campaign, which was, we were invited to participate. So the Eureka Atomic was held off Barbados in the winter of 2020 in January, February. Included 4 aircraft, 4 ships, island-based systems, and a bunch of other stuff. The original emphasis of Eureka was on shallow convective clouds and the climate sensitivity of climate models. The U.S. involvement featured no observing assets and our traditional cooperation with other labs and universities. We also were interested in shallow convection, but we were interested in mesoscale coupling with the ocean and aerosol cloud things. And some of the NOAA effort is less on climate change, on more climate variability. Several NOAA labs participated and a bunch of universities you see listed there. And the NOAA's climate program put out a call for proposals for participation. Next slide, please. So the goals of Atomic were measuring properties of atmosphere, ocean, and air-sea interactions. And we were interested in a number of physical mechanisms associated with those interactions, surface waves and fluxes, surface currents, winds, how clouds and even river outflows affect the ocean properties and ocean stratification on a variety of scales, spatial and temporal. And we want to get a really good data set for satellite validation and satellite algorithm development and also future modeling studies. Next slide, please. So this is the 10 projects funded by the NOAA Climate Variability Program, flux measurements from the Ron Brown and the UAS efforts. There was surface drifters, sail drones, aerosol measurements, P3 aircraft studies, several sampling of the ocean, swift buoys, wave gliders, and cloud observations, precipitation. The modeling projects included modeling of coupling of clouds and convection, mesoscale ocean atmosphere modeling with a emphasis on LES, another mesoscale ocean modeling on slightly larger scales, observation and analysis of fluxes, and a PSL reference effort in ocean atmospheric coupling. So next slide, please. So the NOAA platforms that were employed, the NOAA Ron Brown ship, the P3 Orion aircraft, there were 5 sail drones, which was joint NOAA and NASA, 2 wave guiders, a whole bunch of surface drifters of various types. And the Raven UAS, the original plan was to deploy a UAS from the Ron Brown, but the contractor was not able to get it certified for operation from the ship, so we went to Plan B and deployed this Raven from Barbados. Next slide, please. So the Ron Brown, we had 35 days at sea with the 6 drifters deployed during 2 legs, 2 wave guiders with about 30 days each. We had a tower on the front measuring fluxes. We had Doppler LiDAR, Doppler radar, ceilometers, aerosol systems, launched 185 balloons. The P3, we had 11 missions, 320 dropsons, 185 AXPTs. We had a cloud radar, wave measuring radar, oxygen isotope measurements, and we used all the P3 instruments like cloud, microphysics, etc. 5 trail drones were deployed for about 100 days. AOML put out 10 special drifters for surface drifters and the 38 UAS flights from Barbados. Next slide. So this just shows some of the stuff on the Ron Brown. So hit the button there. So the middle there shows the track of the Ron Brown. There were supposed to be 2 cruise legs. There turned out to be 3 because somebody got sick and we had to take them back to Barbados. And the easternmost portion that was out where there's a flux reference buoy called NTAS. Then on the left there, hit the button again, I guess. Yeah, so on the upper left, you can see instruments on the Ron Brown. There's 2 vans for aerosol measurements, another van for the cloud radar. There's a Doppler LiDAR there. The lower left is a wave glider. It's powered by the ocean waves moving up and down through those slots there. There are several different kinds of drifters you see there in the middle. Further to the right is an underway CTD, which measures continuous profiles of temperature and salinity upper 100 meters. And then there were regular CTD and balloon soundings. Next slide. So this is an example of the coordinated missions. You see the Ron Brown track on the left there, and on the right is a blow up when it was out at 51 degrees longitude. There's the Ron Brown there, that's 33 RO. There's 6 swift buoys in the water, they're the SW Swifts, 2 wave gliders, and then that line there shows the track of the P3. We came out, we did a circle around the Ron Brown and dropped 12 dropsons, went down to the near surface, then went back up. And then off on the right of the track, you'll see a bunch of race tracks, which were level legs done in clouds at different altitudes. So this was in this particular flight, we didn't drop any AXPTs like many of the others we did. Next slide. So that completes what I'm talking about for the moment. So hey, Hyodae, you can go ahead.
Yeah. So next few slides will be about the modeling work. So Atomic has strong modeling component has been integrated from the beginning of the program with developing science plan and sampling strategies. So it has a strong process modeling component, and this process model simulations, of course, targeting the process that we identified and or characterized from the field campaign. So therefore, we use those data from the campaign to initialize the model or validate the model. So therefore, we hope to improve the model physics and parameterization, and which can be used for large-scale climate models. So we have, as Chris mentioned, we have 5, I think, modeling component. I think today I'm going to talk about 3 or 4 modeling elements here, which range from LES in the atmosphere clouds to LES in the ocean boundary layer, atmospheric boundary layer, and then slightly larger scale regional climate model simulation based on circulation model focusing on sub-mesoscale or larger scale mesoscale process and wave ocean interactions, wave wind interactions. So I'm going to go briefly one by one, a few highlights of the modeling sort of process and goal, and hopefully in the end I can integrate these modeling efforts into one slide. So, so this is a project being led by Jan Kazil and his postdoc Ping Ping and his collaborators using the LES modeling in the atmosphere to look at the cloud state simulated by this LES model compared to what was measured by Ron Brown and other state-of-the-art analysis called ERA5. So what they are doing is very interesting because they have this so-called Lagrangian LES simulations, so they can move this LES domain, in this case 25 by kilometer over this box, and they move this domain following the ship, and they initialize the model with Ron Brown data, so radio zone and in the free troposphere, and also large-scale circulation forcing will be from ERA internet, but it can move this LES domain following the ship track and then make a continuous comparison with ship measurements. So I think they did really interesting work, and when you do that from, so they already did this LES simulation for this Ron Brown track, and then show that, in this kind of water vapor and the relative humidity up to 400 millibar where this LES model is running is relatively in good good agreement with the Ron Brown measurements. And there are some interesting difference between ERA5 where they try to attribute the deficiency in ERA5 in representing low-level clouds in this case. And they had this simulation of surface heat fluxes, latent sense of heat flux for their simulation period, and they show some differences between model ERA5 and LES, and then shipboard measurement of their fluxes. So I think they are try to investigate what causes this difference, and hopefully they can lead to improvement in the surface boundary layer parameterization. So this is the work being led by Peter Sullivan at NCAR, also Beck Williams and Lionel Renault at UCLA. They are doing very impressive LES modeling work, and this is truly amazing, actually. So this is an atmospheric boundary layer LES simulation, about 20 kilometer length in the zonal direction, and about, I think, 30 kilometer in the meridional direction. And they put this system temperature jump here at the white line, and then observe the boundary layer response to this SST condition. And what is being shown here is a movie is a vertical velocity in the boundary layer. You can see that when the SST is prescribed here front and wind blowing from left to right, they use some sort of very fancy method called fringe method to circumvent the issues that usually LES model have this with this double periodic boundary condition. But so when you prescribe the upstream condition, you can see this downstream development of this vertical velocity field, for example, that can extend well beyond 20 kilometer, even 30 kilometer, 40 kilometer. So this is a very interesting but also challenging problem, because when you measure things locally at SST flux and boundary layer property, the real big impact is on the downstream, depends on the strength of the background winds, right? So we need to be able to measure something farther downstream of this of the SST front, and that that was I think that was discussed in the science meeting before the field campaign, how we best sample this kind of a sort of non-local downstream evolution of the boundary response to sea temperature front. And they are doing similar thing for the ocean boundary layer simulation, where I'm not going to go detail, but they show that when this when you have this very fine scale frontal eddy, cold filament, they can interact with the winds and wave to generate these sort of characteristics that are different from traditional Langmuir circulation here. So when the wind blows from, in this case, low to south to north, and away from the front here, you can see these cells are generally aligned with the wind direction. But when you go away close to the front here, this is Rossi number close to almost 20. So this is huge frontogenesis happening right here. And these Langmuir cells tend to be more zonally oriented in this case, and that's due to this frontal instability. So this is very interesting and very informative earlier simulation that are highly relevant to the atomic program, because as to how the ocean front interact with the wind and wave and boundary layer process to characterize the spatial temporal scale of the response. This is another project. It's the same project, but it's being led by Jim McWilliams and Lionel, also Peter at NCAR. And they have done very interesting work all over the place in the world, actually. Look at the SST, how the SST on the major scale impact of winds, and how does that compare with the surface current impact on the wind stress. And they show that, you know, atomic region is tend to be a very strong area of a coupling between ocean and atmosphere driven by mesoscale fields. So that motivates them to develop very, very impressive couple modeling simulation here. So this is their model domain, 500-meter resolution in the ocean, 2-kilometer atmosphere. So you can fully resolve some mesoscale process in the ocean and some coupling with the atmosphere at 2 kilometers. You can see this is vorticity field generated by this model. So it's beautiful. Look at this North Brazil current and rings and cyclonic eddy and anticyclonic eddy and this loop current. You can see all kinds of interesting feature here. And the idea is that when you have this highly resolved ocean feature, what happened to atmospheric boundary layer and surface winds through the coupling between SST and wind, and also coupling between wind surface current and wind. So they have done some parameterization testing to find the best combination of the physics to use. So it's great. So other work model users like me just take their choice and then just run the simulations. So they're looking at the cloud response and boundary layer responses, how those responses differ with the different types of layers coupling. So so this is a final part of the modeling work. This is done being at WHOI. I'm the PI along with Caroline Clayson at WHOI, and we have postdoc CJR is working most of this work. The two major goals is the one is to quantify the impact of the mesoscale eddies on the air fluxes and boundary layer processes. So we have a bunch of observations in sail drones and the shipboard measurement of the flux and some drifters too. You can see this impact of the ocean eddies and currents on the boundary layer. So what are the impact, size of and magnitude and distribution of the air fluxes driven by mesoscale eddies in this region? And then if you know that from the observation, what aspect of the model, like PBR scheme and surface layer scheme in the atmosphere or ocean mixing scheme in the ocean, what aspect of those model parameterization should be improved to better represent those processes? Not just ARC heat flux, but mostly the thermodynamic and kinematic profiles of the boundary layer, so they can impact the clouds and radiation, stuff like that. So again, we have a bunch of very, very good observations that can be used with high resolution climate models. So this is one example where SST one filament passing over this location from the high resolution climate model. And then this is a time series of system temperature and time series of boundary layer. So you can see that as the warm eddy passes over, boundary layer tend to increase with some lag, but then this increase of boundary layer is punctuated by some episodic collapse of the boundary layer, and that's due to the cold pool event. So there are some interesting physics that SST impact the boundary and moisture profiles, but then they can lead to sort of intrinsic and change in atmospheric boundary convective processes. The second part is, I think, what I'm most enthusiastic about is try to improve the core bulk flux parameterization in terms of wave dependent formulations. So core 3.5, it currently has this wave dependent parameterization. You can take the input from, say, models or buoy about the wave, say, significant wave height, so that's wave stiffness, or wave age in terms of phase speed. And depends on the wave information, you can adjust the roughness length of in the bulk formula, and then they can influence the ARC fluxes of heat and momentum. The issue is that those these formulations are being tested only in a few locations in the extratropics. And I don't know if this wave observation has been used in this, especially in this kind of trade wind regime, low to moderate winds, and how those wave conditions in this region can impact these air fluxes. And I think there's some uncertainty as to how accurate this wave-dependent parameterization is in this region, or generally trade wind region. And because we have so many eddies here, North Brazil current and rings energetic current, and because sometimes there's a swell can be important part of the wave climate here. So sort of local usual assumption that we make is a wind wave equilibrium. So like a wind work done by winds on the wave is locally consumed by, say, breaking wave and dissipation by the wave. But that linear assumption, equilibrium assumption, might be violated in this region because when you have a strong currents and density fronts, they can affect the wave climate and flux on the nonlinear state. So, for example, when you have a density front, they can change the wave stiffness, and then it can increase it affect the refraction of the wave and things like that. So so wave state can depend on the ocean mesoscale and sub-mesoscale frontal variability. So those processes are not taken into account in the core bulk flux algorithm. So we have a data here. Swift, drifters, and wave glider provide some wave information. So and you're going to be using that along with a WaveWatch model, and the coupling WaveWatch to the Wolfram's regional coupling model, and try to refine the core algorithm and see the impact of it. So the issue here is that this is kind of unusual situation where we have a field campaign already happening in year one. This is a 3-year project. Normally, field campaign is year 2, and year 1 is devoted for pre-planning, and the year 2 is experimental, year 3 is integration. But field campaign already happened in year 1, and first 6 months of year 1, we spent greatly on developing sampling plan, science plan. And the field campaign is completed in January, February 2020. Now we are doing this model data integration while the models are still being established. We just finished a bunch of sensitivity tests to find the best physics combination. So it's kind of some unusual setup that, I think we have a bunch of data available, but models are not being set up yet. So that's a disadvantage, but at the same time, this gives you ample time to integrate this model data and then science as well. And we have enough time to improve the model physics and actually set up the model according to what we observed in the observation field campaign, and then plenty of time to disseminate the result through the improved parameterization. I should say that collaboration with the international Eureka community is hugely beneficial. I think they are doing very complementary analysis and modeling effort, and it's extremely synergistic, and we benefit from this such collaboration. Model data sharing, do you want to do that? We haven't discussed this at all. Even between the team members of that, individual PI can generate the model output and share the data with the community. Is there anything that we, as a team, we want to do as a data sharing approaches? So last point I'd like to point out is that this is a process-oriented modeling effort. So all the modeling effort funded by Atom is process modeling. So somehow, eventually, especially year 3 maybe, has to be coordinated with a broader modeling community where, say, if you improve the bulk formula in this part of the region, do you want to implement in the global climate model and see the impact on the large scale and other trade wind regimes? So this is where maybe you can PSMI panel. I know they will be very, very happy to help with this coordinating, connecting with this atomic team with maybe national modeling centers to do some sort of coordinated modeling effort. So I guess that's what I have here. And Chris, maybe you can finish up with this slide.
Yeah, okay, Chris again. I just jotted down a few thoughts from the field program. One was coordinating 4 ships, 4 aircraft, 3 UAS, dozens of UAV, 4 balloon sites was a major issue. The aircraft, the people who flew the airplane were extremely uncomfortable with flying their aircraft through this sort of maze of hazards. And that was one problem. Another is this is a large field program, and there was sort of complex scientific issues, and to some extent, there were some conflicts. For instance, people who are interested in studying eddies and people who are interested in studying air-sea interaction in clouds out well away from the continent. The eddies were near the coast, so we had ships that were more separated than was optimum. We had a mix of new technologies. By new, I mean we weren't using them 10 years ago. Sail drones, drifter arrays, a couple of ships had tethered kites on board, and then there was a new UAS capabilities that we're not used to doing. The communications was a real nightmare because all the airplane and ships are used to communicating different ways. We attempted to get a unified communications method that all the platforms used. And we went through XChat, Planet, and 2 or 3 others. By the middle of the field program, we had it pretty much under control. The data archiving is a real problem here because there's so many platforms, and each platform has 4 or 5 investigators on it. And most of the investigators, people like me, are used to processing the data and producing certain data formats that we like. So it's turned into a real problem about how to do a unified archive with some reasonable coherence between all of that. So the process that we're going through with Atomic is we're trying to have all the investigators produce data sets with DOIs, so mostly NetCDF formats. And we're working with the Eureka people to try and get consistent naming conventions. And the hope is that this data will be easily accessed by standard methods like DODs and that kind of stuff. And then finally, is the overall science integration is a major problem, as you can imagine, because the funding ends after 3 years, and that'll probably have us about a third of the way through the total integration. So that's it for me on comments. I think we're done.
Yep. All right, thank you. We are, it's 10:33, so you both did a nice job of staying on time. Jenny, do you have comments? Do we take some questions from the broad audience before going to closed session?
Yeah, looking at the participant list, it seems like we only have a couple from outside the panel. So if we just want to go directly into discussion, I don't think there is any need in kicking anyone out unless those people have any dire need to speak up and have a question in. So I think let's just go into discussion and see where it takes us.
Okay, let's see. Maybe I'll use this opportunity to ask a fairly simple question. This is for Hyodae for the modeling. So there, you mentioned 2 projects using Rovs to study various aspects of the coupled issue. So you gave some information about horizontal resolution. Do you have any idea what is the vertical resolution of the Rovs, like the upper ocean vertical resolution in either of these studies?
So That's a very good question. I don't know what they're doing for this UCLA group in terms of vertical resolution in the boundary layer. So I don't have a good information about it. I assume they use fairly high resolution as well because they want to look at this. I mean, because whole focus of this simulation is to look at the impact on the winds and boundary layer process. So I assume they use fairly high resolution. In my case, because we are directly asking the PBL process and wave impact on the boundary layer, say wind profile, my idea is that we want to use an extremely high vertical resolution within the, say, so typical boundary layer, lowest layer of the PBL is about, say, 700 meter to kilometer. What if you get down to like 10 meter where surface layer physics is usually invoked? Because otherwise 700 meter and 10 meter, there's a huge difference in the profiles of wind that we have to assume sort of similarity theory to assume the profile of the wind and other properties. So what we are trying to do is to have this like say 10 meter versus 100 meter lowest model layer, right? And see the impact of the boundary layer properties and profiles and impact on the ALC fluxes. I think that's a very, I think it has been done by some wind farm modelers where they use lowest layer at the bottom at 2 meter even, and they use a huge impact on the say stable boundary layer conditions where things don't mix very well and then you need a very high resolution right at the surface. So that's sort of what I'm trying to do here.
And what about the ocean model? What's the vertical resolution in the ocean model?
I don't know again about the UCLA detail about the ocean model resolution. Our case, I actually haven't talked too much about ocean vertical resolution ocean model, but my previous study I used fairly high resolution to represent the diurnal cycle of SST. Diurnal warm layer. Here is diurnal cycle relatively weak, at least in the winter time. But I suppose, you know, I don't know. I suppose I think Greg Force, the drifter measurements show that very good diurnal cycle of 0.2, 0.3 degrees Celsius along the coast. So I suppose vertical resolution near the top will be very important to capture that. So yeah, I think it's a good point. I think about it.
Thank you. Yeah, so thank you. I'll open it up to whomever else has additional questions.
So this is Amy. Can you hear me? Yeah, okay. I was just wondering, you talked a lot about the regional modeling and a little bit about how this could be applied to global models, but what do you think are the challenges in taking parameters from these observations and modeling studies on a regional scale to global climate models?
Very good question, Amy. Surface flux parameterization. I think when I was in the panel, we discussed a lot about this core algorithm or bulk formula, right? That's one of the key uncertainty in the climate model simulations. And like I mentioned, core algorithm, which is widely used by models, especially in the wave formulation, is validated in the very few locations. I don't think it's validated at all in the Tradewind regime. Maybe Chris might correct me, but it's less validated in the kind of moderate wind Tradewind regimes. So I guess if you improve that on the regional scale and represent it in the global model, I don't know, hopefully it can improve the tropical, Tradewind regime simulations relatively better. But that's where I probably like to get some better idea about how we can connect to these large scale modelers, right? Presumably resolutions and model configurations are so different from regional process modeling versus large scale climate scale model. So I don't know, we might need some bridge to be able to do that, but I guess that's kind of the direction that I'm thinking about.
Do you think that there's a way to use some, I guess I've been at the NCAR AI meeting this week, and so I've been thinking a lot about it, but do you think there's a way to take machine learning techniques to use the parameters that you've created in this smaller regional scale and apply it to something that doesn't take quite as much resources as running the full global climate models, but a way to statistically come to those global parameters?
Yeah, I think that's a good idea. I think you can take the, say phase space from the global model simulations and then do some AI types of, I don't know, I haven't done anything like that, but I guess that's kind of something we can discuss among the team if there might be some expertise to do that.
All right, thanks.
Thank you.
Hyodae, I have a related question related to what Amy said. Yeah, I think the big issue with these process studies is to connect the detailed measurements in one specific region to this broad scale. Ultimately, we really want to improve the climate models. I mean, there are many processes, many things that we would like to do, but that's a very important one. And so another question I have, so Amy focused on the spatial scales, but also in terms of temporal. So here we have observation over a couple of months period, I think. And you mentioned in one of your examples that, like for example, this modeling work that Jim McWilliam group is doing, where I think some of the results are dependent on the background conditions. So the things in the North Atlantic change. There is interannual variability and maybe decadal variability in the Atlantic. So how do we know whether these measurements taken in this particular 2 months can be representative of maybe conditions? So if we change the parameterization, is that valid all the time?
Yeah, that's also a very good question, actually. So the field campaign again is 2 months, less than 2 months. I guess that's related to maybe Amy's question, whether we can sample some sort of phase space of different climate regimes, different variability, and then apply some sort of the finding that we have from this specific field campaign. I guess that could be one way to address that issue. Yeah, this kind of atmospheric boundary response, the say length of the downstream response heavily depends on background wind speed, which varies on internal time scale in this region. But I guess yeah, I don't have a good answer to that question other than one other thing is that some of the assets, I think it's like Saildrone is still running in the ocean there, right? I think, Chris, is that right? Yeah, so I think that provides some sort of longer term data set because it's still out there and then transmitting the data. So I guess that, you know, that helps a little bit in terms of the overcoming the short duration of the experiment to look at the hopefully, you know, half of the seasonal cycle or maybe full seasonal cycle. But I guess that's where process modelers are doing, like bunch of, you know, given the parameterization, given the observation we have, you can play with the different pulsing and the conditions to see the impact on the various spatial temporal scales. Yeah. Thank you for the question.
I'll ask, this is Charlotte again. I'll ask a question to Chris. So one of the things that as a panel that we try to gather information on is best practices or lessons learned during these process studies. And you talked about the challenges in communicating across different groups and platforms that about midway through the campaign, you had sort of gotten things under control. Can you speak a little bit as to what was helpful? What was sort of your solution? What practices did you put in place to really facilitate this?
Well, the Eureka people had contracted with this company called Planet for communicating between the ships and the aircraft. And so the atomic people decided we would do the same thing. So NOAA paid for the Braun Brown and the aircraft to have the Planet systems. But Planet came in a variety of levels of service, and it turned out that it was we had problems with the ship and the aircraft, and we finally solved the aircraft problem by getting a box from Planet to hook into the P3's computer system. And the trouble is NOAA is very paranoid about putting other people's software and hardware onto their computer systems for security reasons. So it took a lot of work to get the approvals, and that solved that problem. But that system didn't work all the time, and also one of the aircraft didn't have it, and so for some reason, and it was that was a problem because the P3 doesn't like to fly around if there's an aircraft out there. I don't know where it is. So I have to say, we didn't start soon enough on that, and we didn't really have a way to test it until we got to the field. And that was kind of a problem. It turns out that WhatsApp and XChat were more reliable, even though they're like 20 years old.
Thank you. That's interesting, but I'm glad you have a good workaround with those apps.
So this is Mike. Can I hop in? I had my hand up. So hi, Chris and Hyodae. Thanks for that nice overview. I have a couple questions. Oh, I have a couple questions, but the key one I have regards how quickly you were able to assemble this project and the impact that might have had then on multiple agency investments, and then some of these coordination and science integration issues that you've mentioned here. So I think it's great the investment that NOAA made in this effort, and but would additional time have helped with perhaps getting multiple agency participation, getting the modeling centers maybe more engaged with the effort, and and the like? Just comment on the time frame for this and how you worked within those constraints.
Right. So we actually should have started 1 to 2 years earlier, but we got involved because the Europeans invited us, and from the day they invited us, and we started working on it until I made a pitch to my laboratory, and they said, "Oh, that sounds like a great idea." It was only like 3 or 4 months, so probably I'm going to blame the Europeans. They should have invited us 2 years earlier. Then went and did some multi-agency briefings, which you might have been involved in 1 or 2 of them, and we were really kind of late for the agencies like ONR, NASA, NSF to really turn the ship and pick up with us, because usually they don't have $10 million lying on the table in case Chris Farrell comes along with a great idea. So that was another part. We were actually really lucky that the NOAA's climate program agreed to do an RFP for atomic, because we caught them kind of flat-footed, and they really had to decide really quickly they were going to do it. It was, I wouldn't say it was impromptu, but it was they were not comfortable with how short the time frame was. So in a way, I guess it's just lucky we managed to do it and it was such an incredible success. But at least another year and maybe 2 for something this size would have been better.
Then just a quick follow-up question regarding the international collaborations. Were there challenges that you have experienced in the field? Again, maybe because of the short time frame for getting things coordinated, but also on the modeling side here, what's the other modeling? Who are the other modeling groups internationally, and how are you coordinating with them on both the observational field campaign and then as well on the modeling?
Yeah, so I can go first. I think So one of the PI, Lionel, is at UCLA. He's part of the Jim McWilliams project, but he's actually physically based in France, and he's involved in Eureka OA components. So he's kind of a liaison between the US component and European component, and from which we are collaborating. I guess I think Sabrina is also having this coordination call, modeling call. It didn't happen yet. I think it's happening sometime in July. So we see what kind of modeling work is being done there, and then we go from there. But I guess so far it hasn't been, at least as far as I know, I wasn't involved in this direct coordination of the model work between European and US component. Chris, is it? I don't know whether Chris wants to add something to the modeling side too.
Well, the coordination with Eureka has been interesting because to some extent, it's like what model you choose to do. So we could go out there and do atomic and kind do an own thing, and then there'd be like separate Eureka atomic things. But we went the other way to make as strong a coupling as possible, and that including we're going to try joint archive with the atomic and the Eureka people. So, and when we were in the field, we attended their daily briefings and their planning sessions and all that. So we're going to try and make atomic and Eureka as integrated as possible. And one of the main reasons for this is kind of selfish from our point of view, because we all agreed to like a common available data. The data is available to everybody, atomic and Eureka. And since they got 3 times as much data as we do, we think we're coming out ahead on the deal.
Yeah, that if I can make a comment, that sounds like a good idea because, yeah, talking with Sabrina, it sounds like the French ship was the one that was allowed to go into the closer to the coast. And so most of the observations, I think, were taken by Atalante. And so I think having, in the modeling study to look at the effect of ocean eddies, I think it's very important to have access to those data.
Agreed. I mean, the dropsondes, for example, from all the ships and all the radiosondes have all been put into one giant pool. And we're working on a paper with a DOI for all the soundings, that kind of thing. So
is there a one-stop a website then that the community can go to for their data?
Say no right now. There will be at least a one-stop place where you can find everything.
Mm-hmm.
And we're doing the atomic data in a couple of stages just because it's easier that way, and partly because you can't squeeze level 4 data out of everybody on the same day. So we know it's going to trickle in. So we're going to have level 4 net CDF stuff. There'll be an archive at PSL. There'll be, DODs you can easily access, and then that's kind of a staging, and so once we're satisfied with that, then we're going to be either linking it or simply transferring it to the Eureka site. And Eureka's switched their idea about how they're going to do it about 3 times. So it's just as well we haven't rushed ahead. They did have a site called AERIS, AERIS, where all the data from the field work in real time was going in of varying types. So including model output from the European models. So that was a good central location, and there's tons of stuff in there. Yeah, the data has been a lot more difficult because we're really going on after this idea of actually making level 4 data available to everyone in sort of a unified format. So it'll be a lot easier for people to use.
What's the time frame for that? Do you anticipate?
Well, we're hoping to have most of the atomic stuff done by August.
Okay.
Because we've scheduled a data telecon meeting. It was originally going to be a meeting in Boulder, but then we got COVID. So we have this meeting scheduled for like the middle of August. And so that's sort of the hammer we're using to get everybody to process or to put their level 4 data out and then try and to be applying for DOIs.
Right. Well, so please do keep us apprised of that so that we can advertise that with the community when you feel that the data sets are sufficiently posted out for their access.
Yeah, we haven't thought too much about that, I have ashamed to say, but that would be an important thing to do. It will be, I mean, we're not keeping it closed. It'll be open. And I'm not sure how we're going to advertise it.
Okay.
Okay. Do we have any other questions for Chris or Hyodae? We're coming up on 10 or 5 minutes before the hour.
I have another question, if it's okay.
Sure.
I have a string of them, actually. So in terms of the end point for these 3-year projects, is there conversations with NOAA then, in another follow-on round for integration and synthesis projects? And what's the prospect there?
I'm almost afraid to broach the subject, partly because there was the Eureka people want to go out in the field again in a year or two and do a summer field program, which would be a very smart thing to do because the summer is totally different from the winter with a lot more easterly wave activity and spawning of hurricanes, and the convection you have more deeper convection. I don't know if the U.S. community wants to do that or not, but that would, if we go back to NOAA for that, then we're kind of shooting ourselves in the foot for more money for this. I guess I don't have strong feelings, but I remember Toga Core, for example, and Dynamo both had follow-on announcements of opportunity, and that was huge for those programs. So I think it would be a great idea.
Right. So on that, I would recommend that on some level, you guys think about what the needs are for that second phase of projects. I mean, I think one of the great benefits for this investment by agencies in the field work and the initial modeling projects, the real payoff occurs, as you might agree, in that second phase of synthesis project. And so we've been in conversation with the agency managers for several years now on the importance of that second phase. And so, it can't hurt to engage on that conversation, and also to give the heads up. I think Sandy Lucas, for example, is aware that there's discussion of a second Summerfield campaign, and the degree to which the Europeans drive all of this scheduling, I guess, needs to be taken into account. But given the need for long lead planning and some competing ideas for future field work in the Pacific and further north in the Atlantic that are coming online and will develop over the next couple of years, it's important to maybe float your ideas out there, as well as the potential for engaging, if Atomic and Eureka were to do a summer experiment. I can imagine that NASA and NSF may have interests in that work. So giving the earlier heads up to agencies, and US Clybar can help potentially arrange for such a briefing So,
Okay, yeah, just to say my own opinion is I don't think the optimum thing to do is to go out in the field again in a year or two to do a summer thing, partly because we need more time to spin up more agencies, and partly because we need more closure on the field program we just did. And I mean, in the past, the second announcement for opportunity has been much more heavily slanted towards modeling and trying to bring in our current process modelers and more of the next level up of, I don't know if it's operational model, but whatever the terminology is. That would be what, I would think you would way to do. And the observationalists would be expect a lot less, a smaller share of the funding, and their work would be slanted more towards analysis and how that helps the modeling development.
Okay, well, we are right at the top of the hour. And I think unless Mike has any more questions, I just want to extend a thank you to Hyodae and Chris. This has been really interesting. And I personally really look forward to taking a closer look at some of the observations that have been collected and seeing results from some of these modeling studies. They already look really compelling, and just I lost track of time listening to your talks because it all looked so interesting. So thank you both very much for your time.
Okay.
Yeah, thank you.
Thanks a lot.